So good afternoon. I had the idea of inviting Marcello for this talk after seeing a talk by Ozawa-san, where I thought he hit upon the topic that Marcello is somewhat an expert in, and that is Subramanian geometry. And I thought, rather than just putting the two in touch, why don't I just ask Marcello for more of a pedagogical introduction to the subject? So I specifically asked him not to focus on his recent research results, but rather just to give a flavor and to tell us and explain to us what this is all about, why it's interesting, and how maybe to analyze this. And what is nice is that it connects notions from geometry and analysis. And whenever you have connections, usually these can be exploited to someone's advantage. So even if you come more from the geometry side or more from the functional analytic side, usually there's something to learn. All right. So with that, I'll leave the rest to Marcello. Let me admit the last two people. So Marcello, feel free to go. There's also no time restrictions, so you don't have to rush in case it takes a little bit longer.
So thanks a lot for the invitation, and thank you all for joining. I hope I will live up to expectation about being pedagogical and not go too much into technicalities. In fact, I've cheated a little bit. So I have tried to make a pedagogical talk that goes through some of my results in the area, because I think that they provide somehow some reasons why it could be interesting to also look at the Subramanian side of things. And during the talk, I will go also a bit out of my comfort zone, in the sense that this relation with magnetic operator that I'm going to pop in while we talk is something that I did read a long time ago, and I'm restudying again for a work that I'm doing with my new PhD student. So I am not yet completely aware of everything that is there, and surely I am not familiar with the inner details of the most recent works. But the point of this talk is to introduce Subramanian geometry, introduce the spectral geometry on Subramanian geometry then, and try to motivate why I think it's interesting to study this subject also for mathematical physicists, people interested in, for example, spectral theory of Schrödinger operator, or in general spectral geometry. So without further ado, let me try to give you set up a bit the expectation for how the talk is structured. Since I'm trying to be pedagogical, I want to try and give an introduction of Subramanian geometry, which is as simple as possible, with simple and clear examples. We will see that some of these simple and clear examples are actually connected to many open problems. Keep in mind that there is a lot that I'm not going to say, and that I'm not going to put any proof, but I have given last year a micro course on this subject, around 3 hours, at the Dutch Differential and Topology in Geometry seminar. So if you want a bit more details, but not too much, you might also find something there. And there is also a big reading list. So I will mention some open problem, but there is a lot more that I won't be able to mention in a limited amount of time. Once we have introduced Subramanian geometry and geodesic flows on Subramanian geometry, so the classical side of things, we are going to look into the sub-Laplacians, how we generalize the concept of Laplace-Beltrami operator and Laplacians to these manifolds. And there I will put some of my results, and I will try to motivate why I think it's interesting, even if you don't care about the geometry or the Subramanian setting. And then I want to conclude by showing somehow an old result from the 90s by Montgomery, which has been retaken to life recently, that shows that there is a very deep connection between certain semi-classical limits on surfaces for magnetic Schrödinger operators and Subramanian geometry. So let's move on. Before I introduce Subrimanian geometry, I also need to give you a warning. You might know all of this already. So Subrimanian geometry is the name that I think was given by Strigarts to this field, but it is known in different ways to different communities. So if you know about Carnot-Karateodori geometry, which is Gromov's school of thought, if you know about subelliptic geometry, if you know about non-holonomic geometry, which is the most used term in the Russian school, for example, if you know about singular Riemannian geometry, then you already know what I'm going to talk about, at least from one specific perspective, but they are all the same things. And again, if you are aware, familiar with the work of Hermander on hyperelliptic operator theory, you will know a lot of the things I'm going to say. If you are familiar with harmonic analysis only group, again, you would see a side of the picture that is more or less, is if not the same, extremely closely related to what I'm saying. And the same with affine control theory and non-holonomic mechanics. So there might be things that you know, but by a different name, and it could be worth exploring what is the link. And in many cases, you think that you might have already seen with a different name. So what is Subramanian geometry? Let's try to define a Subramanian manifold starting from an example. So let's take the iso-area problem. What is the iso-area problem? We have some volume, some number that we want to keep fixed. And we consider a curve and space that encloses that volume. And then we ask, what is the shortest path that fixes that gives us that volume? So there might be many different curves that enclose the same volume. One is very thin and very long. One is very large and very fat, and one is wobbly like the one that I plotted. We want the shortest one. So if we look at the concept involved, it's about minimizing the length of a curve. So this integral of x dot square plus y dot square in dt, by keeping the area, the integral over dx dy fixed. Now we work a bit with differential. We can rewrite this two form as the exterior differential of x dy minus y dx. And if we write it in that way, we can discharge the differential on the boundary, and we would get the integral over the curve of this one form. So this line integral is going to give us a way to represent both the length and the volume just in terms of the curve here. We could already try to minimize the problem from this point of view, but it's actually much simpler if we decide to extend the space. So the idea is that instead of living in the two-dimensional flat space, we keep track of the area. We lift our curve in 3D, and we just say that at each point, we add a third point that is exactly the volume that was enclosed by the curve up until that point. What do we gain about this? We have basically complicated our example a priori. Well, let's look again at the objects of the study. We have this new variable z, which is the volume of our object up to a certain point t. So we could compute that. So we can compute that as the line integral over our curve of that one form that I've written the previous slide. But this, another way of seeing this constraint on the z, is that we have a non-holonomic constraint that connects the derivative of z with the derivative, with a certain relation between the derivatives of our curve. So you can see this literally just derived with respect to t, then you get a dot here, this curve goes inside, and then you have the derivative with respect to t there. So you have z dot is equal 1/2 xy dot minus yx dot, which might resemble a rotor to some of you. So another way of saying exactly the same thing is, instead of taking the derivative with respect to time, remove time altogether and look at it in terms of one forms, in terms of the differential. Then this identity here is telling us that the z minus 1/2 x dy minus y dx has to be 0. The z is equal to 1/2 x dy minus y dx. Or in other words, that the velocity of our curve, which is what the one form is, has to be in the kernel of the form dz minus 1 x dy minus y dx. And so somehow this clarifies even more explicitly that rewriting the problem in 3 dimensions and having this special z that encodes the volume has actually made given us a constraint on the velocities that we are allowing for our curve. Somehow the curve has to evolve in a certain way if we want z to track the area of our the hour enclosed from our curve along the evolution. So my claim is we have just defined a geodesic problem on a Subramanian manifold. Let's see, our new ISO area problem, our new formulation of the ISO area problem is telling us that we are looking for curves into R3. So our world now is larger, it's R3, whose velocities are admissible, leaving this particular subbundle of the tangent bundle. So in this subspace kernel of the one form alpha, okay, we want the fixed endpoint just because that's how I defined my curve at in the original way, and such that the length, but beware, the length of C is minimal. And this is important. This length here somehow was forgotten about Z. It knows about a smaller part of the space. It doesn't care about the rest. So this is what I'm saying is the length of gamma is now not x dot plus square plus y dot square plus z dot square under square root. It's not the usual Euclidean length of a curve in 3D, but it's something that takes care of a smaller subspace. And the velocities, they live in a smaller subspace. So a submanifold, a Subramanian manifold, is the triple of these 3 objects. We have an ambient space, R3, which in general is some smooth manifold. Could be a sphere, could be an N, could be a cylinder, could be whatever you like, a torus, an N torus. Then we take a vector distribution that is a subbundle of this tangent bundle. And so we are not taking the whole possible tangent vectors, but we're saying that at each point we have a selection of tangent vectors that is allowed. And we have an inner product, G, that is defined on this subbundle. So in the Riemannian case, G would be defined on the whole tangent space. You take 2 tangent vectors, G allows you to take the scalar product of them. In the Subrimanian case, you are just living in the distribution. You care about velocities in the distribution. Everything else in the tangent space doesn't exist for you. Once we have these 3 objects in place, our ambient space, our restrictions on the velocities, and a way to take scalar products, compute lengths or angles there, we can define what are admissible curves or what is called horizontal curves. Those are exactly those curves in our ambient space, such that their velocity belongs to the distribution. This is what is in this picture here. At each point, the velocity of the curve belongs to the corresponding distribution. And then the length of our curve is the length of the curve with respect to this metric on the distribution, which makes sense now because we said that the curve is admissible. So we know already that all the velocities will be in that plane, and our metric G is defined just there. So our inner product is just defined on those T. So now the question is, how do we know that these curves exist? How do we know that taken any 2 points, we can find this admissible curve joining them? And once we have settled that problem, how do we know that we can actually solve the ISO area problem? How do we know that we find this length minimizer for that Subramanian space that we have defined? Now, before getting there, I want to start looking at the properties of some famous examples. I will mention 2, but we will have already figured out a lot before we come to the second. So let's look. Let's look at the iso-area model. I said my ambient spaces are 3, and I said that the distribution is the kernel of this 1, 4. Another way of looking into it is by taking 2 linearly independent vectors that span that space. So you can check that if you give those 2 vectors, if you feed the one form with those 2 vectors, you will get 0. So they belong to the kernel, and you can also check that they are linearly independent. So we have a basis for our distribution, which is a 2-dimensional vector space spanned by 2 vectors. If you take these 2 vectors and you take their commutator, so if you look at their commutation relation, you find out that you get a 3rd vector out. And this vector is linearly independent with both of those. So the commutator of objects in that kernel escapes the kernel. This means that if you combine those 2 other vector fields, so if you evolve a bit along one of the vector field and bit along the other and come back, then you're not back to the same point. You have this degree of non-holonomy that is essentially telling you, yes, you have moved a bit in the 3rd direction, the one that was not allowed. And this is a key property. So it's really crucial here that once we take into account also the commutators, then we span the whole tangent space. So our curve point-wise lives in the distribution, but if it moves smart, it can move everywhere. And if you look at what it looks like here for the iso-area model, you see if you live here and you start at 0, you can only move on this horizontal plane. You can go diagonal where you want, but you are flat. You can't go in the Z direction. However, if you move a bit in one of those, then you can move a bit high. And then you can see how this moving around allow you to achieve the direction, because your plane are all skewed and they do not form a nice foliation of the space, which is my next point. So it is really crucial that we are as far away as possible from being integrable. In an integrable system, what happens is that the distribution, when you commute the vector in the distribution, they remain in the distribution, which means that however you move, you won't escape it. You won't be able to achieve the extra directions. So in this picture from, I forgot to write it down. This is from Wikimedia in Germany. The other picture I made myself. If you move here, or if you move here, there is no way that from this point you can go down to this point downstairs. You're forced to live in the foliation. This is what you see in an integrable system. And for us, this is exactly what we don't want. And this is also where the relation with the non-holonomic mechanics is coming into play. We have non-holonomic constraints, and we want them to be as non-integrable as possible in some sense. Let me give you one more example, which will come back around the end of the talk. So take a monocycle. And I'm giving this example because all this theory has a nice perspective also from the point of view of control theory. So if you look at the control theoretic part and the optimization part, usually one of the first example with the supersymmetric and iso-area problem is also this monocycle. As you have a point in space, and then the wheel of your monocycle is pointing in some direction theta. The position can be anything. My monocycle could be here, could be here, could be here, could be here, and my wheel could point here, or it could have pointed here. It's a monocycle in space. But because it's a monocycle, what you can do is turning your wheel, which would be this vector field here, or move along the direction in which you're pointing, which would be this vector field here. This is the vector cosinus theta, sinus theta. So when you pick theta, you're moving in that direction. And if you look at the span of those 2 linearly independent vector fields, that's your distribution. The nice thing about this model is that since their commutator, again, is not in the distribution, it's the orthogonal motion. It's minus sin theta cos theta. It's the orthogonal vector to that motion. It means that you can actually achieve any direction in the end. And this is, for example, what gets into play if you want to know how you can parallel park your car. You can't slide your car into the position, But because the motion of the car is made by two non-commutative vectors in their distribution that escape the distribution, then it allows you to achieve the orthogonal distribution with some effort. You have to go forward, turn your wheel, go backward, turn your wheel, which is exactly doing the commutator. And again, if you look at the picture of what this vector field look like, you see that, okay, you have a motion in one direction here, but if you want to go, if you want to achieve motion in other direction, you will have to go up, turn your wheel, and then move. Because if you are here, you are stuck moving always in the direction of your wheel. Or if you take one that is like, so again, you can somehow see when you look at your vector field that there is not a nice foliation of the space, but things are twisting in such a way that by moving around, you can achieve any direction. Yeah. And this is the crucial property. I will probably spend even too much time on it, but I hope that the pictures and explanation kind of justified why it's so important. So this is called the Riemannian condition, and we will see in a few slides why. And what it's telling us is that we want this to happen. We want that a finite number of commutators of vector fields along the vector fields in our distribution will span the tangent bundle of our manifold. So at every point, the tangent space is completely spanned by enough commutators of your vector fields. A distribution that satisfies the Riemannian condition is usually called bracket generating, but you can find completely non-integrable, totally non-holonomic, Lie complete, I think. There are, I've seen 4 or 5 names for this going around. But what it tells you is that, okay, if I take my distribution and I take a lot of commutators of my distribution, I just need a finite amount of them and I can reconstruct the whole tangent space, which means I can achieve any direction. The number of commutators that you need, that is what's called the step of the distribution. So distribution of step 1 doesn't need any commutators. Distribution of step 2 needs 1 commutator, and so on and so forth. And finally, we arrive at why this bracket generating is crucial. It's because when you have a bracket generating distribution, for any point, you find a ball in which any 2 points are connected by admissible curves. And the way you achieve this is exactly what I was mentioning. Because of the degree of non-commutativity, if you look at the flows along these vector fields and essentially compute its their commutator, you move along one, along the other, back along the first, back along the other, then you will have achieved the extra direction you need, if you need it, to connect those points. The thing that one needs to take care of or be aware of is that by doing this, you need to take more effort. Somehow this is something that comes down at higher order. And this is important because okay, this is actually something I won't get much into. Those are all spaces that are not non-homogeneous. So you will have, for example, in the case of the iso area problem, which is the Heisenberg model, we will see, if you look at the group structure, you will find, and the dilation, you will find that the dilation are not homogeneous of order 1, but are 1 in the first and second coordinate and order 2 in the second coordinate. This non-homogeneity comes from the fact that in those directions, you have to make more effort somehow. I know I'm being very vague, but if I go in that direction, then it would be 1 hour just talking about that. So now that we know that we can basically cover the space with balls and connect with admissible curves any 2 spaces in each of this ball, we can actually change the process. And so if we have 2 points that are far away, we just take enough balls, and then we compute admissible curves. It turns out that if you take the infimum of the length of all the admissible curves joining those points, you find a well-defined metric. You you find a well-defined concept of distance between those points. Now, the objects you get are not nice in the following sense. What you see in this picture above is a model we will discuss later. Those are balls. If you take the filling of the exterior boundary here, this is a ball of radius 1 centered at 0 for our model. And this zigzag here, it depends from loss of optimality, but it's something we won't get into. Again, we'll take another seminar just to talk about that. But you see, even just a ball can look horrible. It has corners here. And at this point, it's usually not even Lipschitz continuous. So even balls, spheres, using this Subramanian distance can be horrible. And there are lots of conjecture related to those. Okay, I can come back if you want at the question time, but we find a well-defined metric, which completes somehow or start making our geometric picture nicer. We have a manifold, we have a structure in it. With the structure, we can construct length minimizing curves, and we can use them to define a metric on the space. But the object we get is not that nice from the regularity point perspective. There are some nice perks that comes with the Choraczewski theorem, which is that the metric space M with distance has the same topology of M, and that the distance is finite and continuous. And in fact, the theorem like Oprinov hold also here. So there is this duality between the complete, geodesically complete manifold and complete as a metric space. But let's not go there yet. So we have defined our geometric object, and we have now seen that we have a well-defined metric on it. Again, this is, I've been torn until the end if I wanted to put these example slides, because I think without picture it's a bit empty. But if you're familiar with contact geometry, for example, contact structure are an example of Subramanian manifold. Grushin plane, which is, yeah, this is something actually is worth telling. Look at this Grushin plane. We are in R2. Our distribution is the span of dx and x dy. So almost everywhere, our distribution is the full tangent space. However, when x is 0, we lose this vector. So if we want the full tangent space everywhere, we actually need to take an extra commutator to be sure that we can get rid of this. The fact that this distribution changes rank, it goes from rank 2 to rank 1 in a sub-manifold, this is called not equiregular. So the distribution is equiregular if it has always the same dimension, and not equiregular if it loses dimension. And this can happen. They are both valid. They are both bracket generating. But not being equiregular creates a huge amount of problem. There is one more thing that is interesting, is the Barthes structure here, which has a y squared. So you need twice the bracket, the commutations before you can take out the dz. And this also comes with a series of extra complications. And finally, I don't know if this has a name. This is just an example of a non-bracket generating structure. There is no way you can get this z out of here. And so at z equals 0, you won't ever take the tangent space. So this is not a good Subramanian manifold. And the other, if there are experts on topology, or if you are, for some reason, have been into contact with contact mechanics and angle structure, quasi-contact structure, was just to show that those are all examples of submanifolds that are actually quite explicit. And in many of those, we know very little from the Subramanian point of view. There's lots of work to be done. But let's go back to us. Before we can define our sub-Laplacian, I need to tell you something about geodesics. So geodesics are just the length minimizer. And if we were in the Riemannian world, things would be nice, because we can somehow represent them in a nice way with the Levi-Civita connection. We can look at the Euler-Lagrange equation, and we have a unique parameterization from the initial speed. So we have a set of well-defined differential equation on the tangent bundle that tells us, okay, given a point and a velocity, you have a unique geodesic that goes up there. And we have a nice Hamiltonian formulation that is dual to this Euler-Lagrange equation. Now, the issue here is that this is all gone. In Subramanian manifold in general, there is no torsion-free connection. So we can't have Levi-Civita connection. This is out of the picture. The other problem is that the unique parameterization is gone because our vectors are in the distribution. So any vector that is not in the distribution will give you a geodesic, but it gives you a geodesic that couldn't coincide with the one that is projected along the distribution. So you will have infinitely many vectors that would give the same geodesics. So that's bad as well. So what can we do? Now, why I moved this here? I wanted to move this later, so forget about the slides. So what can we do? We can rewrite this whole thing as a constraint minimization problem. So an actual problem from control theory, and then use Pontryagin maximal principle to actually write down an Hamiltonian that describes our geodesics. If you want, we can go in the details of the construction, but again, this is something that would take away a lot of time, and I want to discuss Laplacian, so I'm going to omit that. But the important point is that we can actually lift the problem of finding this constraint, these length minimizing curves with constraint on the velocities to an Hamiltonian on the cotangent bundle. And that is a genuine, well-defined Hamiltonian. So instead, our Hamiltonian lives up here. It's defined in this way, is the momentum applied to the vector squared and to the vectors that span the distribution. And the projection of the solution of that Hamiltonian flow, so if I take the Hamiltonian flow for the vector field associated to this, those projections are going to be geodesics. And in this way, we can associate uniquely a covector to a geodesic. The problem with this procedure, if you know how Pontryagin principle work, is that there is also a set of admissible minimizer, or it can be a set of admissible length minimizer, which are critical point of what's called the endpoint map for our flow. And those are not seen by the Hamiltonian. So there is a set of curves that you cannot describe as solution of your Hamiltonian, which are also solution of this constraint minimization problem. And this is a big issue. You have two different types of geodesics now, if you want. You have the normal geodesics, which are the one that you see from the Hamiltonian perspective, and you have the abnormal geodesics, which are the one that you see from this other critical points perspective. Now, these abnormal geodesics can be normal. So there are some that are both Hamiltonian and the critical point of this functional, but there are also things called strict abnormal that are just the critical point of this functional. And for those, I will give you an example. But let's look at what this Hamiltonian look like first. As I said, you take the vector field that span your distribution, and then you want to compute pxi at the point x, the sum of this. And this is your Hamiltonian. So once you look at what happens here, dx will hit this derivative in x and gives you a px. Then you have minus 1/2, that is the constant is there. And then you have pz, then dz, that will give you a pz. So overall, you get term of this form in your Hamiltonian. You see, this is just a genuine Hamiltonian on the cotangent space of R3. And then you have the second part that gives you by plus x half pz. And if you look at what are the solution of this Hamiltonian, which are the curves that I have drawn here, you see that these curves are going to follow these little planes that I've written here. If I had foliated I wasn't able to do a nice picture with that. I should try more. I was trying to take this kind of planes and put them in the picture, but then it was very hard to read anything out of it. But what happens is that at this point, the tangent vector of this curve is living on the corresponding little plane here. And this is translation invariant in Z, so you would see the same picture all over. And the ball starting at 0, it's just made of all the curves that move like that and go up. You see there are infinitely many here that rotate around and go in. Now, what I hope some of you have observed is that this Hamiltonian here looks very much like the Hamiltonian for a charged particle in a constant magnetic field. So somehow, here we are seeing the component of our magnetic field. Z is a cyclic variable, doesn't appear in this Hamiltonian, so Pz is actually a conserved quantity. And here we get the helicoidal motion in the Z direction, which is exactly what you're seeing here. If you continue this motion, it's just doing this. This is the motion of a charged particle in a field, constant field in the Z, in the Z direction. And if you project it down, you will see the Larmor's orbit on here. In this specific case of the Heisenberg problem, there is no abnormal, no strict abnormal. All the solution, all the geodesics are described by this Hamiltonian. It doesn't take too much to find an example in which you have abnormal. Well, it historically took a long time, but now there are plenty of examples. So if, for example, consider the kernel of this other distribution, you remember the one where there is the y squared, and that y squared giving the step 3 creates a lot of problems. This is one of those examples in which we have issue. So the set y equals 0 is a set in which you don't have the third direction, which you are unable to escape in the z direction. Geodesics described by our Hamiltonian are the one that are plotted in the picture. There is one special one, which is the one that is escaping along this line here, which is a stricter normal. It appears at the critical point of this endpoint map. And one thing that I want to stress is it's actually going to be very helpful when this minimizing curve can actually cross the singularities, this singular curve, and they do it orthogonally. The place where we have really a lot of trouble is when they are tangent to this, like here. Here you have tangency. The velocity is tangent to the critical set. This is where things go wild, also from the analytic point of view. But I'm going to come back to that. So now we are ready to talk about what happens, how to make subablation and what happens to the quantum picture. What we have seen so far is that by putting certain constraint of the velocity and requiring this constraint to satisfy some non-integrability condition, this Ormander's condition, then we can define actually a genuine geometric structure that leads to length minimizing curves, that leads to a notion of metric, which can be related to the metric from the geometric point of view, to the inner product that we have in our manifold. And that we have, even though we lose a lot of the properties of our geodesic flow, we still have a chance of recovering them via an Hamiltonian that is a genuine Hamiltonian. But we just have to keep in mind that there are some bad things that could happen. In the rest of the talk, I want to show you how we can now somehow quantize this Hamiltonian, writing a Laplace operator on our manifold. And at the end of the talk, we will discuss, are those abnormal, those special geodesics that are not seen by the Hamiltonian, actually giving some extra information on the system? And what does this tell us in terms of magnetic Schrödinger operators? So let's go back there. Let's start again from Rn, and let's define a elliptic operator. Let's take a generic second order linear differential operator with smooth coefficients. This is just in Rn. We have a second order component, a first order component, and some potential. This is called hypoelliptic. If locally, for all the distribution, the LU is smooth implies that the solution U is smooth itself. The weak solution is smooth. So it's a generalization of elliptic regularity. Ormander has done, and not just him, has done a lot of work on this. We know that in this case, the principal symbol, which is just the sum of this coefficient with the corresponding momenta here, has to be non-negative. And then we have what are so-called Ormander type operators that are operators made of squared of some vector fields, like what we see here, plus some other vector field, plus the potential. So we call operator on this form, written as sum of some smooth vector field on Rn, product of smooth vector field on Rn, Ormander type operators. Where I'm trying to go with this. Ormander already at this time proved the following theorem. If those vector fields you are using to define this Ormander type operator, so xi and x0, are bracket generating, that bracket generating that I was calling Ormander condition, finitely many commutators of those vector fields are able to recover the whole tangent space, then your operator is hypoelliptic. And now maybe you start seeing where I'm going. Now there is a chance that we can make this procedure work on manifolds, on Subramanian manifolds. And then we have the bracket generation. So if we can make it work, then we would have an hypoelliptic operator, which is our Laplace-Beltrami operator wouldn't be bad at all. So let's see. How do you define a Laplace-Beltrami operator on a manifold? So on a Riemannian manifold, you have your manifold and you have your inner product on the tangent bundle, the full tangent bundle. This inner product comes with a Riemannian volume. So there is a natural volume associated to it. And we can define the gradient just from the inner product as follows. It's the thing that makes our vector fields act on the function as one would hope. So as derivation on that function. Once we pair the gradient at this natural volume that is defined from the metric, then we can define the divergence as essentially the rate of expansion of the volume when you evolve it along the flows. So if you forget about this explicit formula in coordinate and look what the coordinate free definition looks like, then you see this divergence is the thing that tells us how are we expanding or contracting the volume when we move along this vector field X. The Laplace-Beltrami is just a composition of those two. It's the divergence of the gradient, like the operator that we have actually in our end. But now there is the extra thing that this depends on the metric and depends on the volume that was defined via the metric. This is a crucial point, the dependence on the volume. And this is another place where we will see Subramanian manifolds have issues. The volume in the Riemannian case can be determined by the metric. It's the volume of an orthogonal parallelotope in the tangent space being 1. So it's a rescaling of the tangent parallelotope so that the volume is 1. But the metric that we have on the Subramanian manifold has no natural way to being extended in the tangent bundle. There is no way to define that parallelotope and make that metric work naturally there, at least in general. So what is the Subramanian volume? We have a gradient in the sense that that depends only on the metric. We are only considering horizontal admissible vector fields. So this makes sense as is. But this, what about this? Again, this is another place where one could spend an hour. There are many ways of defining volume in the Subramanian one. And even though there is one that is considered to be the most natural, this pop volume, there is not really a definition of natural one. And in the non-regular case, it's just completely open field right now. It's not even known if those volumes are equivalent. Sometimes actually they are not. So in what's going to follow, I'm going to just pick any smooth volume and work with that until I decide that I have a natural one to pick for some example. So this is an extra complication that we get once we have to work with Subrimanian manifolds. We don't have a natural volume to define, and there are many different possibilities. Those are bad. We don't know if they are even Lipschitz continuous. The pop volume in general is relatively regular, so at least it's nice to work with. But there are more. So which one is the natural one is an open question. And there is actual recent research going on this stuff. It's quite a deep question. So given that we don't have a natural volume to choose, and we just have to pick some smooth volume, let's see how we define the gradient. Once we have defined a volume, then we are done. We have the horizontal gradient, which is exactly what you had. This is G of gradient f x. It's exactly what we have in the Riemannian case, but now it's defined just on the distribution. We have the divergence that is again defined in terms of the derivative of the metric of the vector fields, of the volume along the vector fields in our distribution. So it's still the rate of expansion of contraction of our volume when you evolve along that vector field. It's just that it's going to happen on a subset of the vector fields. And the sub-Laplacian then is just the divergence of the gradient. If we now make computations, you can check that this horizontal gradient is just written as the vector field applied to the function, is decomposed as the vector field applied to the function times the vector field itself. So when you use this, then from this operation, you recover the coefficients in this vector field, and you get exactly satisfaction of this definition. So we can write this object explicitly, and it comes here. This is now just a function. So we can use the property that the divergence act on a function times a vector field as the vector field along the function times plus the function divergence of the vector field. This just comes from the definition, this via the derivative. So this is the same as in the Riemannian case. And so what we get when we expand this sum, we get twice the application of the vector fields on the function times the divergence of the vector fields time, again, the derivation with respect to this vector fields. But look who we got back. We have the vector field xi squared, and we have a first order object appearing here. So we got our Ormander type operator. So despite all the complication, despite the terrible geodesic flow, despite all the limitations that we have in constructing these objects, actually we get nice Ormander type operator out. And those are really nice operators. They are symmetric, they are negative on completely supported functions. So you can try to look at the completion, and then you will find that if you have a complete manifold, and in fact, thanks to Ophrino problem, if you have a complete manifold, then you have an essentially self-adjoint operator on the two functions in your space. And then you can go and study it operators, find that there are nice properties, nice contraction properties of the semigroups. So actually you have an object that comes from a very complicated situation, but it is nice to start. So let's look at some example before I tell you what we don't know again. First of all, if you apply this procedure to a Riemannian operator, to a Riemannian manifold, then you get exactly the Laplace-Beltrami operator. So our generalization sounds like it's reasonable. If you take the Heisenberg example, the metric that you have there is just the planar matrix dx dy. The volume that you get there, here you have a natural one, because in that case, you know that there is a left invariant group action that comes bundled into the object, and then you can take the R measure, the measure that is invariant with respect to the group action, and you find that it's just the Euclidean volume and the R3. And with those objects, you get that the Laplacian is actually a nice object like what I've written here. And again, here you might see the hints of a magnetic Schrödinger operator in L2 over 3 with a constant magnetic field in the Z direction. We will come back to this object later, but you see this magnetic field, the constant one at least, that pops up already in a few places. Another interesting example, which I'm going to talk about for the next 5 to 10 minutes before we conclude, is this Grushin on R2. It was the one in which the distribution is spanned by the in the X and the X in the Y. In this case, if you remove X equals 0, in which you lose this direction, you actually have a Riemannian manifold. You always have the full tangent. As soon as X is non-zero, then you have the vector take the X and some constant time the Y point-wise. And so your distribution is the whole tangent space. So your manifold is actually a Riemannian manifold. So we can actually look at the associated Riemannian metric, and which would be the x squared plus 1 over x squared dy squared. And then we can take just the volume associated to this. It's not going to be defined at 0, x equals 0. This is what you see here. But almost everywhere is actually the Riemannian volume on the Riemannian manifold that you have. So the only place where you have issues here is x equals 0. And then you just compute the divergence of the gradient for this manifold. Then you find that it's a nice-ish Laplacian plus blowing up first order correction. So let's make it a bit simpler. And instead of taking a plane like here with x and y, we compactify one of the directions. And so we have dx and x d theta instead. So we have taken the y, flipped it around, and compactified. We have a cylinder. Its geodesic flow is the solution of this, is given by this Hamiltonian, px squared plus x squared p theta squared. You compute the solution of that Hamiltonian, you will find these curves, these blue curves here. So you take the Hamiltonian equations, you compute the solution, and you find, look, we can define some reasonable curve here. Now, what is very interesting at this point is that this S equals 0, this is the singular set, is where we lose this vector, is where things get Subramanian. And geodesics cross that set. So our Riemannian manifold, which is the first cylinder minus this curve, the one that wraps around at x equals 0, that is a Riemannian manifold, which is not geodesically complete, because geodesic can actually arrive at the singularity, cross through. So if you wish, if you imagine that is a ball, that ball is about to tunnel across the singularity. Let me use this terminology. Now, if we compute the Laplacian on this space, which is what I was showing in the previous slides, but with a d theta instead of a dy, what can we say? So it turns out that in this case, you can say that on each half of the cylinder, this is giving you an essentially self-adjoint Laplacian. So if you look at the closure of your operator, there is just one closure, and this is essentially self-adjoint on each of the halves. If you compute solutions, they do not know about each other. There is no transfer or read or information between those two halves of the cylinder, even though the geodesics that are there are actually passing through, and even though this operator here is what you get quantizing this object. This Hamiltonian is actually the principal symbol of this operator here. And then one can ask, what is the spectrum of this object? And you find that it's a continuous spectrum with embedded eigenvalues. And so you say, what is now the limit law for this eigenvalues? How many eigenvalues do I see asymptotically? What is this phi law? Normally, the phi law would compute the volume of your manifold and would compute curvature in phi. But now here, the manifold has infinite volume, and the curvature is blowing up to minus infinity at 0. So what are we seeing if we try to do that? And if you try to do that, you find out that you can still have a meaningful phi law, which somehow measure the Minkowski or the Hausdorff dimension of the singular set. That, okay, logarithm terms are actually related to something else. And we don't really know what this is describing. There is a series of work by Hilaire, Trela, and Colin-Verdier that are trying to figure this out for equiregular, so not for this case, Laplacians, but it's still unclear what are the objects here. And we don't know what is the next term, because it turns out that the next object here is actually a Dirichlet counting problem. So if you solve that, you solve also the Dirichlet counting problem. We don't know what is the next order here. And then why is this interesting overall? This is interesting because you have a manifold with a non-complete geodesic flow whose Laplacian is essentially self-adjoint on each of the connected component of the cutted manifold. And there is a conjecture, recent one from 2020, that says that if you have a closed smooth manifold with a smooth density and a formally self-adjoint operator there, then the Hamiltonian flow is complete if and only if the operator is essentially self-adjoint, which is true in many cases. It's true for complete Riemannian manifold. It's true for complete equiregular Subramanian manifolds. It's true for differential operators, degree 1 circles, differential operators of degree 1, Lorentz and Laplacian. It's true in a large number of cases, but it becomes false as soon as you look for almost Riemannian manifold. We have at least one counterexample, the Grushin cylinder. But in fact, since this is about closed manifold, you can do the same on a sphere. You compactify both X and Y, and you will find that that also has the same problem. You have two halves of the sphere on which the Laplacian is going to be essentially self-adjoint, and yet the geodesics can cross through. So how general is this? It turns out this is actually very general. And if you go and study that and look at a complete Subrimanian manifold with a smooth measure on the whole manifold except on the singular set, and this is complete on M, it's no longer complete on M minus set. It means that geodesic can pass through. There are an incredible amount of examples of this. Then the distance from the singularity is what tells you if you are essentially self-adjoint or not. If this distance behaves in a certain way, as this as a lower bound, then the Laplace-Beltrami operator corresponding to that volume is going to be essentially self-adjoint on each of the connected component of the manifold minus this critical set. And if the components are relatively compact, then the corresponding Laplacian is compact resolved. So it makes sense also to compute the Weil law. And this is one of our results that I wanted to mention. And I want to mention because now we have this abstract thing. It's on the Subrimanian manifold. It's proving that that conjecture can hold in the Riemannian case, but it's definitely false in general for the Subrimanian case. But it comes with consequence on the Euclidean world, on the Riemannian world as well. You can prove as corollaries, I'm not going to write them because they are horrible to read, but they are extremely effective and practical. They are all constructed, you can compute all the terms. You can prove that the theorem that tells you how a potential should blow up around the points that you're removing from your manifold to have an essentially self-adjoint operator, you can generalize it to arbitrary submanifolds of Riemannian manifolds. So if you're removing a line, or if you're removing a plane, or if you're removing some other object, what does the potential need to do around this object so that you have an essentially self-adjoint operator? Further, you can actually show that your operator is self-adjoint only due to the way the curvature blows up. So we have a criterion for self-adjointness that only depends on the blow up of curvature and that allows the curvature to oscillate. And those results are new in the Riemannian case. And sometimes are generalizing results that people were looking for in particular cases because they were just too hard to solve from the other side of the picture. So there is benefits in looking at this. There might be benefits in looking at this generalized point of view. Also, if you care about Riemannian or Euclidean results. I'm not saying that this is always the case. It might be just pure luck. But this is not the only one I can present. I have other papers, and I know of other papers in which by proving something in the Subramanian setting, you could actually increase your understanding and give new result on the Riemannian and the Euclidean case as well. So I believe it's actually worth getting rid of some of the commodities of the Riemannian geometry to actually get to the heart of why certain things happen. Now, even with those theorems, there are plenty of simple examples in which we can't say anything. So for example, if your second vector field has a blow up in one of the variables that is slightly faster than x cubed, then we know nothing. If L is greater than 1, we conjecture that it's essentially self-adjoint, but our proof requires a certain thing happening on a tubular neighborhood of the singularity that can't happen in this case. So you need completely new way of dealing with it to prove it. If you take a Martinet-like example with one tangency point, so a point in which the distribution is tangent to the singular set, then it's not known if the operator is essentially self-adjoint. Worse, all the hard inequalities that people are developing so far are not good enough to say anything about the self-adjointness. And in this case, everything is explicit. You can write everything down explicitly. And this is something I'm not going to talk about, I'll just mention. If you then start and look at the Weil law, that also is bringing up new interesting insight. What does it measure? It seems now that it's clear that the first term is measuring the leading order power is going to measure the Hausdorff dimension of the singular sets. But what do the other terms are doing? This is not known. Now, I'm going to conclude. I know I'm late, but I abused the kindness of Max that I could run late to add a bit more meat throughout the talk. So what about the magnetic fields? I've mentioned that the Heisenberg-Laplacian looks like a magnetic operator. I mentioned that the Heisenberg-Hamiltonian looks like a magnetic Hamiltonian, both with constant magnetic field. So let's take a surface symbol, R2. What I'm going to say is generalizable to Bochner-Laplacian on emission connection, on emission line bundles on surfaces. But it would just require additional definitions to put there, so I'm not going to mention it. Well, no, I'm not going to do it in that generality, but you find it in those papers up here. Montgomery did it essentially what I'm doing here for line bundles, and then Marinescu and Savale generalized it for more complex objects. But so we take this Laplacian, in which I have taken one form that you see here, and that you might recognize now as Laplacian with the magnetic field, which is just the differential of this one form times lambda. So I'm just taking a magnetic Laplacian with a semi-classical parameter lambda that I want to send to infinity. What does this have to do with Subramanian manifolds? Let's repeat the trick that we did for the Heisenberg-Laplacian. In that case, we had those coefficients here times the x and those coefficients here times the y, and then we were doing dz minus the first thing minus the second thing equals 0. Let's just brutally do it. What happens? Let's define the distribution at the kernel of this object. I added a dummy variable theta, three-dimensional variable, and I'm constraining to be minus ax dx minus ay dy. If you remember, the way I reached that from my first equiarea example was that I wanted to keep the area fixed. So you might start connecting this object to the flux of your magnetic field across on the area enclosed by the curve. And you wouldn't be wrong. So if you define this one form, takes its kernel, then you can find out that it's spanned by those two vectors down here. And as a manifold, you take the original plane, and then you have this compact variable on the circle here. Why is this interesting? Well, you see, the third variable in the Heisenberg case, well, the z, which now is a theta, is a cyclic variable of the Hamiltonian. It means that it doesn't appear in the Hamiltonian. Ax and ay are just functions of y and theta, and y and x and y. And so corresponds to a conserved quantity, which you can also see as the fact that actually this operator is computing with the theta, and you can project it down with Fourier decomposition. And once you do the Fourier decomposition, what you get here is that this is giving you an I lambda. And so that your operator splits into a sum of your original operators here. And look, the I energy spectrum here, very large lambda, which is the limit that I was mentioning at the beginning, is exactly the limit that we wanted to investigate at the beginning. What is the semi-classics when lambda is very big? What is giving us the big contribution? This here is the quantization of the Subrimanian Hamiltonian in the sense that I was mentioning before. It's that the Hamiltonian that you have as principal symbol is exactly the Subrimanian Hamiltonian. And now, where is the crucial point here? Is that if you look at the zero locus of your magnetic field, assume that this is a curve. So assume that your magnetic field is zero on a curve. Then what happens is that this curve is actually a local minimizer for the Subramanian metric, but it's one such local minimizer that you cannot find with the Hamiltonian. So it's one of these strict abnormal things. And this paper by Montgomery, this was the first example of a strict abnormal action. And so if you lift this curve to the larger space M or 2 times S1, you have defined strict abnormals. If this is made of many curves, you have many strict abnormals now. And now, why are those abnormals interesting? Is that because the leading order, as lambda goes to infinity, so as the strength of the magnetic field grows, is actually controlled by those. You find that the eigenfunctions are concentrated along this curve. And you find that the eigenvalues are actually controlled by B0, which is the gradient of the magnetic field along the curve. So if this is constant, you have actually this form as the linear term. If this is not constant, then you can just say that this is an order of lambda to the 2/3. Yet you can actually, this was done by WKB, you can actually show that the contribution there all comes from this strict abnormal. So when the magnetic field goes to infinity, the contribution to your eigenvalues are all coming from this strict abnormal. So they do contribute to the eigenspectrum. And another nice side of the problem is that how you then find this E star. The C star is the ground state of an anharmonic oscillator that you get by doing a normal form approximation on the curve. So you go on this zero locus, you make a normal form approximation, you find that your Laplacian, the original one, is close to another Laplacian, which is of Martinet type. So it's the screw up that I was mentioning before, the thing in which we can really say little because there are normals appearing and whatnot. And so to study this operator, which can be studied by other means, you can actually go to the Subramanian side and you can start making sense of many of the objects that you're having from a geometric perspective. And this sometimes might simplify the computation. The paper in which this result is proven is not so complicated. And in fact, this is the end of the talk, but this is just the beginning of this kind of study. Savale and Marinescu and Savale in the last 3 years have exploited this relation with magnetic field, for example, to study magnetic Dirac operators and different kind of topological feature and topological expansion of topological invariants, Bergman kernel expansion for line bundles. Greatly generalizing what was known before. I know very little about these works. They are very topological, but the key there was realizing that you can work with sub-Laplacian, exploit all the sub-Laplacian theory, and then give new result in topology. And then with my PhD student and 2 other collaborators, we are trying to look at Faber-Kranic inequality in the Subramanian setting in order to look at also their meaning in cavitation superconductivity when you have bent curved surfaces. Now, these are just two of many possible things that people can explore. And those two in particular really rely on this fact that you can actually study magnetic operators, even Euclidean one, by lifting them to a Subramanian space. And this gives you a natural way of dealing with them. But there is another side of the picture, and then it's really my conclusion, is that you can think of bringing your knowledge from the magnetic operator, for example, and applying it in the Subramanian setting. Magnetic pseudo-differential calculus is the first that comes to mind. Can we use it in this setting? What new things will it tell us? Does it make sense to use that to actually know more about the Subramanian setting now that we know that we can jump from one to the other? So I hope that it was clear enough. And if it wasn't, please ask me any question. And thanks for your patience.